Hey everyone, this is the second half of the lecture for Tuesday's class, and I'm going to talk now about record linkage, which, as any of you who have worked with economic data know, tends to be a fundamental task. Oftentimes you have data from one source that's on the left-hand side of your regression and data from another source that's on the right hand of your regression. In order to run that regression, you need to link those data sources together. Or maybe you have multiple data sources that go on the left hand or the right hand side of your regression. And this in general is a task that can take up a huge amount of effort, especially when it comes to working with historical data. So, just to name a few examples, researchers and businesses frequently link individuals or firms across censuses and company records. Governments also do a lot of record linkage, deduplicating benefit or voter rolls across locations, which surprisingly enough don't always come associated with IDs, even in the modern period. Maybe you want to seek how information from different sources spreads through the media, etc. Just lots of different applications. And in the majority, the vast majority of the relevant literatures, deep neural methods have not made inroads. And so there is a recent comprehensive review of the computer science, social science, and statistical record linkage literatures in Science Advances. It's called, like in parentheses, almost, and then all of entity resolution. So entity resolution is just another name for record linkage. And they conclude that other methods are preferred over deep neural methods for record linkage and structured data. And so this contrasts to some seemingly very similar problems, such as disambiguating entities and unstructured text to a knowledge base like Wikipedia, which we saw a couple of lectures ago, where transformer large language models overwhelmingly predominate. And so why is it that this review and much of the literature seems to have concluded that deep learning is not applicable to record linkage and structured data? Well, they say, labeled record linkage data sets are very small compared to the massive corpuses that are used for training deep learning models from scratch. And hence, deep neural methods aren't going to be applicable because we don't have enough data to train them. And indeed, it is very costly to construct training data for record linkage. It's a very labor-intensive process, but this ignores the power of transfer learning, that actually a lot of the information that we need to improve the accuracy of record linkage is already contained in pre-trained models. And so just because we don't have a lot of labels doesn't mean that deep learning methods aren't applicable. But we just have to think, and in this review it says with the unstructured text, doing entity disambiguation back to Wikipedia, you can use a large language model because it's unstructured text, and you just can't do that with structured data. And kind of actually in the work I'm going to show you that is not the case. Large language models actually can potentially be beneficial for record linkage and structured data as well. So in joint work with Abhishek Arora, who's a pre-doc, and Chimei Yang, who's an undergrad who's going to be joining our PhD program next year, and Xiao Yu, who you guys have seen in class, who's also a pre-doc with my group. We examine whether deep learning can significantly enhance record linkage by developing a novel multimodal framework that we call clippings. That stands for contrastively linked pooled pre-trained embeddings. And so clippings is motivated by the insight that many record linkage applications can be conceptualized as a multimodal classification problem in which the document image crop of an entity's name and its corresponding text from OCR are the inputs, and each unique entity is a class. More generally, document text and photographs that appear in the document could be used for creating cross-document linkages. And so this is an example of what the data looks like. And so on the left-hand side, we have lists of customers and suppliers of Japanese firms. And we have localized the name of the customer or the supplier in the original documents, and then we have an OCR of it. And you can see kind of in pink, those are OCRs. The OCR isn't perfect. And then we would like to merge these customer supplier lists with a firm index that has lots of additional information about these firms. And this is written vertically instead of horizontally. And again, we have localized the firm names and we have OCRs of it, which do contain some errors. And so the multimodality of this comes from the fact that we have an image of the firm's name, and then we have the OCR text of the same firm's name. But this framework is not limited to applications like this. This is another example that we pursue in this study, which is image and caption pairs from historical newspapers. So historically, newspapers often got their photos from a photo wire, and so the photo would be sent over the wire with a caption, but they would tend to significantly edit the caption to potentially to fit in their space. And then the images could also be edited. Like in this example here, you see that they significantly cropped the image. Also sometimes these images are pretty horrible quality. And so potentially like having both the image and the caption is going to be able to help us identify better which images came from the same underlying photo newswire source. And this is super interesting because kind of we've observed that newspapers might be talking about the same story, but they use very different images to talk about that story, right? And so like in the example of protest, we've noticed this regularity where if the newspaper is kind of supporting the protesters, oftentimes they'll show a close-up that personalizes the protesters, whether it's just showing their face, showing them being beaten on the ground, being brutalized, that really humanizes protesters. Whereas if the newspaper is more opposed to protests, it's much likely to show a big kind of just menacing crowd that maybe looks kind of threatening. You see this huge crowd. And so like, we're very interested in newspapers. They're talking about the same story, but by choosing different images from the photo wire, they can give a very different perspective on the story. And so we want to know which images are the same and which images are different. So why are images useful? Like going back to the record linkage case. Well, this is an example of a firm name that was mis-OCR'd. And, because firm names or people names are oftentimes only a few characters in Japanese, if you get one character wrong, you're kind of in trouble in terms of being able to link that back to a large database with many, many possibilities. Okay. So standard methods for image text classification, which are used for applications like hateful memes and product descriptions, we saw these in the multimodal lecture, use a supervised classification objective. And that cannot be applied to problems like record linkage because first of all, there's a very large number of classes, right? You might be linking to millions of entities. You can't take a softmax over millions of positions because that's computationally intractable. Moreover, the classes might be unknown ex ante. So we have, hundreds of millions of newspaper images and we have no idea what the classes are ex ante. We just want to group them into images that are the same. The classes also might constantly evolve as the database is updated. And so we don't have to, with a supervised classification objective, you just have your predetermined classes. So it can't take into account that your classes may be constantly evolving. So as with unimodal applications, such settings can be tackled by learning a metric space where classes can be assigned using KNN classification or clustering. So this is going to very much like on the last point, it's kind of like I talked about with FOCR, that you can add new characters at inference time. Same thing here, you can add new classes as the database evolves. Okay. And so Clippings employs end-to-end training of symmetric vision and language bioencoders to learn a metric space where the pooled image text representations for an instance is close to representations in the same class and is distant from representations in different classes. And we are going to start the model with CLIP, either kind of OpenAI's CLIP for the English or a Japanese version of CLIP for the Japanese data set. So we start with CLIP, and the reason why we can take a pooled representation, a pooled embedding of the image in the text is because these are aligned spaces. It would make no sense to do that if the spaces weren't aligned because we're just taking the average of the representation, the representation of the image and the representation of the text. And then we're doing contrastive learning on that. And that only makes sense if the spaces are aligned. So actually clip off the shelf is not going to be aligned for this sort of application, because this does not really look like what clip was trained on, which is kind of more modern image caption data scraped from the internet. And so an important part of what we do is we do self-supervised pre-training, either on our image caption pairs, which we have an essentially infinite supply, or on image crop OCR pairs, and that's totally self-supervised because we don't have to create any labels. We just OCR the image, or we already have our image caption pairs from the newspaper. We do self-supervised language image pre-training on that, same objective as clip, to make sure the spaces are aligned, and then we can just either use that, or we can do further supervised training where we have pairs of data, right? So we know one corresponds to one on the left corresponds to one on the right, two on the left corresponds to two on the right. And we do contrastive training on the pooled representations of the image and the text, and it works to pool them because the spaces are aligned. So the baseline uses a supervised contrastive loss where we're just taking the mean of the image and text embeddings for instance I. And so this loss incentivizes alignment of image, text, image, text, and text image representations across positive instances. So it has the flavor of combining contrastive learning on the text, contrastive learning on the images, and this UniCL loss, which has bidirectional image text and text image similarity objective. And so if you come up here and you look at 1-to-1, right, there's 4 possible pairs that you want to align: the image to the image, the text to the text, the first image to the second text, and the first text to the second image. And this contrast, just doing contrastive learning on the pooled representations of one on the left and one on the right, is going to incentivize all 4 of those to align. So at inference time, instances can be linked by retrieving their nearest neighbor from an offline embedding index, or by clustering the representations. And this contrastive framework can flexibly incorporate blocking on database characteristics, which is common in record linkage, by using a type-specific loss. And so there's a very large record linkage literature on how you do blocking, which, say for instance, you're trying to link the 1920 to the 1930 census, and in general, you want to link 20-year-olds in the 1920 census to 30-year-olds in the 1930 census, and you don't need to worry about people who are 20 in 1920 and 20 in 1930, because those can't be the same people, right? And so that's called blocking. And blocking is very natural to incorporate into contrastive learning with a type-specific loss, which we don't do in this study because it doesn't really apply, but that's another big advantage. And so this is just a visual representation of the architecture. And so we have image clips, which go into the vision encoder, and text clips, which go into the text encoder. And these have been aligned to create an aligned space. And so that the embedding created by the vision encoder has been incentivized to be nearby the embedding created of the text of that image by the text encoder. And then we just pool those 2 representations, which we can do because they're in a aligned space. And then we can figure out what name that's linked to by finding its nearest neighbor in either in the offline index. In the case of the record linkage with the Japanese firms, we have an index of 70,000 firms, and we want to find each customer or supplier in that index, which we do by just taking the closest one. Or in the case of the newspaper articles, we don't know ex ante what the classes are, so we just treat it with we just do clustering, and that gives us linked records. And so, as I said, our first application is supply chains, where the firm is represented by the image crop of its name and the document scan and the corresponding OCR. And we're interested in this application because supply chains are fundamental to the transmission of economic shocks, to agglomeration, and to economic development. And their role in long-run economic development has been difficult to study quantitatively, due largely to the difficulties of accurately linking large-scale historical records. We train clippings on a modest number of linked firms using supervised contrastive learning, following self-supervised language image contrastive pre-training on the image crop OCR pairs. So that self-supervised pre-training just continues the clip loss, but with image caption pairs from our data set rather than, CLIP was trained on 400 million image caption pairs scraped from the internet. Japanese CLIP, they just translated the English captions to Japanese and they trained it on that. At inference time, customer supplier records are linked to their nearest neighbor in an offline embedding index that's created from another publication that has firm records for 70,000 firms. If it's above a certain distance, then it's considered a no match. And we do have lots of those, like your customer is just a government agency, for instance, it's not in the firm record. So you can deal with that by having, by just having a threshold. All right. So again, this is just a recap of what the data would look like. And we want to know that firm number 1, which is a customer of another firm, is linked with firm number 1 in this firm index, which has a bunch of other characteristics about the firm and so on and so forth. And so what's the comparison? What's the baseline? Well, people in the literature overwhelmingly use string matching methods. I mean, there is some other stuff. There's a paper on patents using random forests and whatnot. And so there are some other approaches, but string matching still largely predominates. In their simplest form, approximate string matching methods simply count the required number of edits, so insertions, deletions, and substitutions, to transform one string into another. That's Levenson distance. In practice, not all substitutions are equally probable, which leads to a lot of efforts to construct rule-based lists that adjust the cost of substitution. So let me give some examples. There's a package called Fuzzy Chinese that uses strokes or radicals as the fundamental unit for n-gram substring representations of entities, where these strokes and radicals are drawn from an external database covering a subset of the CJK script. And so it breaks each character down into each of the strokes in that character, and then those are n-gram representations, and you look at the similarity of that, and you think this might be helpful because OCRs tend to be homoglyphic. It's confusing one stroke for another. But this only works if the character is in the database, which not all characters are. It's a subset of CJK that people have computed what the strokes are. Another example, there's a package called Masala Merge that adjusts Levenson distance to impose smaller penalties for common alternative spellings in Hindi. Most famously, there's Soundex and this New York State Identification and Intelligence System, and they account for the fact that similar sounding substitutions are more likely in the U.S. Census and in other U.S. records, since census enumerators misspell names according to their sound. So, in Soundex, J-O-H-N and J-O-N, making that O-H substitution would be very cheap because misspelling John as John is kind of a likely error. And this is really fundamental to kind of matching in U.S. Census data. So it's using whether or not these substitutions sound similar. But again, people have extended Soundex to other languages, but overwhelmingly it's kind of been used for English, and it doesn't exist, for all languages. And so these rule-based methods may perform well in the context to which they have been tailored, but they can be brittle, and also importantly, they're labor-intensive to extend to new settings. So this skewed linked data sets towards a few high-resource settings, like U.S. censuses, where there's been a lot of effort kind of made to linking and kind of designing substitutions that are probable, and this skews downstream knowledge. Even in high-resource settings, low accuracy and some applications can require extensive human intervention. If that's the case, it's going to limit the scale of the problems that you can tackle. An additional important limitation of string matching is that it's unimodal, despite a growing emphasis on processing documents with multimodal models or OCR-free vision-only models. Okay. And so that's the alternative, kind of mostly string matching. Like I said, there's some other approaches. People maybe use some random forest type approaches, but that hasn't been like the norm. Most people use string matching and various iterations on string matching and gram matching, etc. So how are we going to train clippings? We have a 60-20-20 train-val test split with a pretty modest number of examples. That's 772 training examples. So that's all the supervised training we're going to do, just 772 examples. But we're also going to have synthetic data. So we took nearly 20,000 Japanese names. We just pulled these out of like a place name dictionary, I think. And we rendered these using different fonts, and we OCR'd them with 2 different OCR engines, so Paddle OCR and FOCR, I think, that make different errors. So this gives us different views of a given image crop OCR pair. So we have different images because we use different fonts, and we have different OCRs because we use different OCR engines on these different fonts. And so this is kind of another source of synthetic training data that is much, much cheaper to create because it's like costly, like quite costly to actually label the data. Xiaoyu will tell you. I'm sure he'll tell you in class on Tuesday about how costly it was. We have that synthetic data. This is for the supervised kind of contrastive training where we're training on the pooled image text representations of the firm names from different sources, one written horizontally and one written vertically. Importantly, we also conduct self-supervised language image pre-training of the Japanese clip encoders, which were used to initialize the model. And here we have over 100,000 firm image crops and their corresponding OCR. And so we just took kind of all the, like a bunch of firm crops from our data set and OCR'd them. And here we're doing contrastive language image pre-training where we're incentivizing the embedding of the image crop of a firm name to be aligned with the embedding, the text embedding of its OCR. And so we find that clipping achieves 94.5% record linkage accuracy. That's compared to a string matching maximum accuracy of 73%, which was from using FOCR, which, as you guys saw in the first half of this lecture, has like a character error rate of around 0.6 to 0.7%. So this is a very accurate OCR. It's about a best case scenario that you can get. But still, because firm names only have, a few characters, if you get one character wrong, you're likely to miss it. And also the other problem with string matching is it doesn't account for language, which is important in linking firm names because there can be different ways to write company or just small differences based on the language of how you write down a firm's name. Like in one source it has incorporated after it, and in another source it doesn't. Again, you could try to engineer rules to deal with this, but when you're working with very large data sets and there's lots of little things like this, it's hard to engineer all those rules. And the language model is going to pick up on that. So particularly in academic research, fine-tuning on a modest amount of labeled data, so we had about 700 pairs, can be more of a feature than a bug because it gives us fine-grained control that's typically the hallmark of scientific research. Yet when we forego supervised contrastive training, so we only do the self-supervised language image pre-training, taking crops of firms from our data and their OCR and just doing self-supervised pre-training of the clip encoders on that, this also outperforms string matching with an accuracy of almost 85%. So even if you say, I don't want to create any labels at all, you can still do better with deep learning than you can do with string matching. Moreover, supervised contrastive training of the aligned vision coder on only images. So we get a vision encoder that's aligned with text, and then we only do contrastive supervised training on that vision encoder, outperforms the same training on an encoder with unimodal rather than multimodal pre-training. And so instead of doing the pre-training with clip, aligning the language image representations, we just do pre-training with a VIT. And when you look at it, when you do vision only contrastive training on the aligned encoder, it gets some things right that require language to get right, even though you're only using the vision. And so when you do this self-supervised pre-training to align the language encoder and the image encoder, your vision encoder is learning about language. And I think this really underscores the power of multimodal methods for document analysis. Okay, so let me now go through these results. And so noisy OCR is GCV, which is actually reasonably decent on firm titles since they use a bigger, bolder font, but not great. And clean OCR is FOCR. And so using string matching methods, you obviously do better with the clean OCR. And the stroke n-gram similarity, that's the fuzzy Chinese package I mentioned, and it doesn't do kind of much better than just sort of straight up Levenshtein distance. And the reason for that is not all the characters are in that package, even though in principle it helps with homoglyphic errors when they are. Okay, panel B is only doing the self-supervised training. And you can see when we use the pooled vision language embeddings, we get up to almost 85% accuracy. And it doesn't matter if you have a noisy or a clean OCR, because now you have the vision encoder. So even though your text is noisier, it just doesn't matter, or it doesn't matter much at least, because you have that vision encoder. Okay, if we do supervised training with only vision pre-training, so there's no language in this model, this is just using VIT to do vision matching, we get about 88% accuracy. And basically in looking at the output of this, we get everything you can get with just the visual appearance of the firm name. So this is what happens when you totally eliminate the OCR information bottleneck, but it's not able to use language to understand, okay, this firm has incorporated at the end of it and this one doesn't, but they're the same firm. And then finally with the supervised training, we get up to almost 95% accuracy. Again, you do a little bit better with clean OCR than with noisy OCR, but you're kind of narrowing that gap a lot because you have the information from both the original image and from its OCR. These are some ablations. So if we just use zero-shot clip with just the vision encoder off the shelf, it does horrible because it hasn't seen images of images of text. It's just a language encoder. It's kind of better, but not great. And so really what panel A shows you is that using clip off the shelf is not aligned for this application. We need to do our additional language image pre-training where this is still totally self-supervised, but we're training it on our text OCR pairs, and we get up to 85% versus being at 43 just by aligning the image and language encoders for our application. Panel B is if you only do supervised training. So forget about panel B, which is the self-supervised language image training. We just take this model in panel A, the zero-shot Japanese clip, and we do supervised training only on it. And it's not great. It's still maybe, like, it's not even better than, I think it's not even better than just doing the string matching. And the reason for that, again, is it doesn't make sense really to be pooling the language and the image representations if the space hasn't been aligned. And so this self-supervised pre-training, where we incentivize the model to create a similar representation for the image of a firm's name and the text of its firm's name, that's an important part of this process. This is the error analysis, and I think this is kind of instructive. And so the panel A, the first one is error made by the vision only encoder that clippings gets right. And so this is a case where the two things look very similar, but one character means pharmaceutical and the other character means confectionery. So like in the language sense, they're not similar. And so having a language model here is really helpful. The second one is one that the language only gets wrong, because the language only, the two names are very similar, but you can see with the vision only, they don't look as similar. And so that's where having the image helps, as well as having just the OCR of it. And the third one in panel A is one that the multimodal model, as well as I think the vision only and the language only models get wrong. Everything gets this wrong. And it's because you can see that these two firm names are very homoglyphic, like the characters in them look very similar. And then it's just somebody's name. And so there's not really a language signal to go off of either. And so it's just like a pretty tricky example. Panel B is kind of interesting in that this is showing things that the VIT gets wrong, that clippings gets right. And I won't go into the details, but this is the clippings vision only encoder. And this kind of indicates that when you do that language image pre-training, even if you're in a scenario where you don't have the OCR and you just want to use the images to do inference, having done that language image pre-training, the model acquires some amount of language understanding from it, and it's making errors, like it's getting things right that you would get wrong if it only understood vision. even though it's only had the supervised pre-training on vision. That language image pre-training really helps a vision encoder to have some understanding of language because it's forcing the vision encoder to align with the language encoder. This is what the input-output networks look like. This is noisy OCR with Levenshtein distance on the right, and on the left, and clean OCR on the right. And you see the degree centrality is proportional to the size of the dot, and the shading is just the distance to one of the big three pre-war Japanese firms. And I think the biggest thing that stands out on this graph is you see the position of these dots, the firms, is fixed. So you see a couple of like big false positive nodes on the left, which are just like a bunch of things get linked to the wrong firm. And so the picture, like really the picture is substantively different, with the graph on the right being kind of much closer to the ground truth. And so when you have noisy record linkage and you're only getting 64% or whatever, 62% of those links correct, it really is kind of likely to make a difference to your downstream analysis. Okay, so clippings does not model cross-modal attention. And there's two reasons for that. So first, we don't think it's necessary because, at least not for the Japanese matching, because we have like an image of a firm's name and then the text of the firm's names, and those are both a view of like exactly the same thing. Whereas if you remember, if you go back to our multimodal lecture where we were talking about having cross-modal attention, and so like this example that you see here is a case where it's trying to classify the sound that is being made, where there is from video, so there's an image and sound. And so like the dog barking, like it's paying attention to the dog's mouth, or yodeling, it's like paying attention to that person's mouth. And this just doesn't enter our application because it's just views of the exact same thing in two different modes. We don't think it's so useful, and it would be way more costly to run and more complicated to train. And so we're already at like almost 95% accuracy without it, and we don't see a way that it would help with the things that we're getting wrong. And so I think it really makes sense when you need to kind of attend to a very specific part of one mode with the other mode, and that's just not something that applies in our context. Okay, more general applications. So we'd like to test whether clippings can apply to not only document image clips in their OCR, but also images and text more generally. So we apply it to this case of historical newspapers, where we want to know which image caption pairs in this very large corpus came from the same underlying photo newswire source. A lot of papers got their images from the Associated Press. There's also like a wire for the United Press. And they got captions, but they tended to oftentimes significantly abridge or modify those. They could also significantly crop the image, or the resolution can be really, really poor because these like came over first a telegraph and then later a telephone wire, and then they're scanned, and there can just be pretty poor resolution. And so we find that clipping significantly outperforms popular string matching methods. This is just a recap of what the data looks like. This is really something that we did in a couple of days as a proof of concept. So we think we can get the accuracy up significantly if we just especially do the self-supervised pre-training for longer on more data. We just didn't have time. But you see, even in this initial proof of concept, we're beating string matching on the captions. And so we think that there's a lot of promise here. We're obviously interested in the downstream applications of using this to analyze things like I mentioned, the protests that are kind of super interesting social science questions, but it also has kind of applications directly to machine learning research. So duplicates in training data significantly increase the regeneration of that training data by large language models and by stable diffusion. And that raises copyright and plagiarism risks. So there's been a paper showing that stable diffusion is like quite likely to just exactly regenerate images that are duplicated in its training data. And they can also contribute to test set linkage. And so clippings is a potential tool for deduplicating large image caption data sets. All right. And so just to sum up, multimodal methods can significantly improve record linkage while remaining highly scalable. Compared to methods that predominate in the record linkage literature like string matching, deep multimodal approaches can leverage the power of transfer learning, facilitating their application to highly diverse settings with modest annotation requirements. We saw even just doing the self-supervised pre-training performs better than traditional string matching methods. And I think if we had more compute to do self-supervised pre-training for longer on more data, it would probably even close the gap further with the supervised approach. But in an academic application, creating a modest number of labels is not actually too burdensome of a thing, and it really gives you the fine-grained control that you might need. All right, so future directions and takeaways. We focused on image text linking. We're interested in applying this to the case of record linkage, where rather than using kind of the fact that the firm names, that you can get information from language, using the fact that names, like people names, are misspelled according to their sound. And so we'd like to extend it in that direction. And are doing some initial thinking on that. Moreover, deep multimodal record linkage offers potentially substantial gains in a variety of settings where the traditional string matching methods fall short of the required accuracy. And we think this is particularly true in low resource settings, where the kind of the hacks to string matching methods that I showed you that take into the account that some substitutions are more likely than others just don't work well, or maybe where the OCR is horrible, so they're going to work less well. And so we hope that deep multimodal record linkage can potentially broaden the diversity of applications that are feasible to study, and can also improve the quality of the data for downstream applications. So that's all I have on record linkage, but I'll really look forward to talking about this in class on Tuesday. Thank you.